A cone is a three-dimensional geometric shape that tapers smoothly from a flat base to a point called the apex or vertex. More precisely, it is the solid figure bounded by a base in a plane and by a surface formed by the locus of all straight-line segments joining the apex to the perimeter of the base. The term cone sometimes refers just to the surface of this solid figure, or just to the lateral surface. The axis of a cone is the straight line, passing through the apex, about which the base has a circular symmetry. In common usage in elementary geometry, cones are assumed to be right circular, where circular means that the base is a circle and right means that the axis passes through the center of the base at right angles to its plane. Contrasted with right cones are oblique cones, in which the axis does not pass perpendicularly through the center of the base. In general, however, the base may be any shape and the apex may lie anywhere. A cone with a polygonal base is called a pyramid. Other mathematical meanings. In mathematical usage, the word cone is used also for an infinite cone, the union of a set of half-lines that start at a common apex point and go through a base. An infinite cone is not bounded by its base but extends to infinity. A doubly infinite cone, or double cone, is the union of a set of straight lines that pass through a common apex point and go through a base. Therefore, double infinite cones extend symmetrically on both sides of the apex. The boundary of an infinite or doubly infinite cone is a conical surface, and the intersection of a plane with this surface is a conic section. For infinite cones, the word axis again usually refers to the axis of rotational symmetry. Either half of a double cone on one side of the apex is called the nap. Depending on the context, cone may also mean specifically a convex cone or a projective cone. Further terminology. The perimeter of the base of a cone is called the directrix, and each of the line segments between the directrix and apex is of generatrix of the lateral surface. The volume and the surface area for a straight cone are described in the geometry section below. The base radius of a circular cone is the radius of its base. Often this is simply called the radius of the cone. The aperture of a right circular cone is the maximum angle between two generatrix lines. If the generatrix makes an angle theta to the axis, the aperture is 2 theta. An elliptical cone is a cone with an elliptical base. A generalized cone is the surface created by the set of lines passing through a vertex and every point on a boundary. Cartesian coordinates. In the Cartesian coordinate system, an elliptic cone is the locus of an equation of the form geometry. Surface area. The lateral surface area of a right circular cone is where is the radius of the circle at the bottom of the cone and is the lateral height of the cone. The surface area of the bottom circle of a cone is the same as for any circle. Thus, the total surface area of a right circular cone is radius and height. Where is the radius and is the height? Radius and lateral height. Where is the radius and is the lateral height? Circumference and lateral height. Where is the circumference and is the lateral height? Apex angle and height. Where is the apex angle and is the height? Volume. The volume of any conic solid is 1/3 of the product of the area of the base and the height in modern mathematics. This formula can easily be computed using calculus. It is up to scaling the integral without using calculus. The formula can be proven by comparing the cone to a pyramid and applying Cavalieri's principle, specifically comparing the cone to a right square pyramid, which forms 1/3 of a cube. This formula cannot be proven without using such infinitesimal arguments, unlike the two-dimensional formulae for polyhedral area, though similar to the area of the circle, and hence admitted less rigorous proofs before the advent of calculus, with the ancient Greeks using the method of exhaustion. This is essentially the content of Hilbert's third problem. More precisely, not all polyhedral pyramids are scissors congruent, and thus volume cannot be computed purely by using a decomposition argument. The volume of the cone is also related to the summation of square numbers. Center of mass. The center of mass of a conic solid of uniform density lies 1/4 of the way from the center of the base to the vertex, on the straight line joining the two. Right circular cone. For a circular cone with radius r and height h, the formula for volume becomes where r is the radius of the cone at height h measured from the apex. Thus, for a right circular cone, the surface area is where is the slant height. The first term in the area formula is the area of the base, while the second term is the area of the lateral surface. A right circular cone with height and aperture, whose axis is the coordinate axis and whose apex is the origin, is described parametrically as where range over, and, respectively. In implicit form, the same solid is defined by the inequalities where more generally, a right circular cone with vertex at the origin, axis parallel to the vector, and aperture, is given by the implicit vector equation where or where, and denotes the dot product. Projective geometry. In projective geometry, a cylinder is simply a cone whose apex is at infinity. Intuitively, if one keeps the base fixed and takes the limit as the apex goes to infinity, one obtains a cylinder, the angle of the side increasing as arctan, in the limit forming a right angle. This is useful in the definition of degenerate conics, which require considering the cylindrical conics.